if you want to find the volume of some region, but you know how to find areas, as hopefully you should, then one way to get volumes is by making parallel slices. So for instance, if we have a cylinder, you'd like to know what the volume of this cylinder is, given that you know its height is h and its radius is r. Well, perhaps what you need to do is to slice this in along a parallel plane. And that slice will have a certain thickness. And that thickness, for instance, might be something you call delta x. And so the volume of this circular disk is whatever the area of its cross-section, let's say as a function of x, times delta x is the volume of this slice. And so if we want to find the volume of this region, all we need to do is get slicing. And so now that we've sliced this up, the thing to do is to say the volume of the cylinder. It's a sum. It's a sum of the different areas times delta x for I is equal to 1 to n. Now, of course, we should probably think of this as a limit, because that delta x in this case here is just fine because the cylinder is all the same cross-section. But in the case of a more general object, we ought to take the slices to be thinner and thinner and thinner. So we ought to have a limit as n goes to infinity. And of course, this thing here as a limit is a Riemann sum, or in other words, an integral. From some starting x to some ending x value. And so if we put the pieces in here, well, what is the area of one of these little cross sections? Well, it's pi r squared times dx. There's no x in here, this is a constant. So this is pi r squared x. Those endpoints, or put in other words, pi r squared h, which is the usual volume of a cylinder formula. Okay, but volumes by slicing work for other shapes, not just cylinders. You just take this picture and slice some other way. So for instance, let's find the volume of a pyramid with a square base. And with these volume problems, it is always a good idea to draw a picture. So there's my pyramid with a square base. A square has got side length s, and it's got some height from the center to the top. Let's say that the height from the center to the top is h. So we want to slice this, and you could slice this in various ways. You could slice it vertically or horizontally or some other slice, maybe parallel to one of the faces. I think the easiest slicing, though, is slicing parallel to the base, because then each cross section that you get is a little square-shaped region. Of course, it's actually like a truncated trapezoid kind of shape. It's actually got a name. It's called a frustrum. But you don't need to know the fancy term in order to do the technique. The technique is pretty easy. The technique is going to say the volume of this pyramid. Let's say that this direction is z, and it's going to go from 0 to h. A is a function of z, dz. All right. Notice that the z starts out at 0 at the base and goes up to h at the top. Now, what you then need to do is figure out what the area, cross-sectional area, is. Now, if you look at the cross-section of this pyramid, you'll notice that when z is equal to 0, the area is that of a square, and the side length of that square is s. When you get up to z equals h, the side length is 0, and so there's no more area. And so, really, it's something squared, because that's the area of a square. And in particular, when z is equal to 0, it is s, and when z is equal to h, it is 0 that we're squaring. This quantity is the side length. As a function of z. All right, so how do we find that? Well, it's a linear kind of thing. It starts out at s, and it decreases with increasing z, and by the time we get to h, we've lost all of our s, so that is the formula. Notice if I put in z equals 0, I just get s squared for the cross-sectional area. Good. If I put in z equals h, I will get a 0 squared for the cross-sectional area. Perfect. And then, of course, you can evaluate this integral. It's not terribly hard to do, and I will leave that to